Hello everyone, welcome to another episode from Chedexcel. Today I am going to talk to you about how we can write the electronic configuration of atoms or ions. So the last video I discussed how electrons are actually present inside an atom. So I will put a link and you can see of the pop-up banner the last video about existence of electrons of an atom. And normally we use three basic rules to fill them. Now in Chedexcel they won't ask you to write those three rules, but they expect you to memorize those rules. Means they expect you to remember what each rule imply or what it says. The Pauli exclusive principle, Hund's rule and the Aufbau principle, all three are required to write the electronic configuration of atoms and ions. So let's say let's try to write the electronic configuration of atoms. Let's say hydrogen, the very first atom. So hydrogen has only one electron, so that is filled into the 1s according to the Aufbau principle, and each orbital can have maximum 2 electrons. So we write it as 1s1. So if you draw it 1s1, it's like this. Then we will write helium 2 electrons, 1s2, the same. That's it. So because S subshell has only one orbital, each orbital can have maximum 2 electrons and those are spin parallel and opposite to each other. Okay. Then lithium third one. So then 1s2, you can't write 1s3 because S subshell has only one orbital, each orbital can have maximum 2. So after 1s is completed, according to the Aufbau principle, it should be 2s, 2s1. Then beryllium fourth one, 1s2, 2s2. Then boron fifth one, 1s2, 2s2, then it goes to 2p, then 2p1, like that. So if I write something let's say nitrogen 7, 1s2, 2s2, 2p, 2p3, that's how it 3 comes. If you ask to draw this one, 1s2, 2s2, 2p3, 1, 2, 3. Remember, according to the Hund's rule, each orbital should have one electron before they are going to paired up. So you have to have one electron at least there. That's how we draw. So likewise we can draw let's say sulfur, which is 16. So I just skip many. 1s2, 2s2, 2p6, after 2p, because p can have 3 orbitals, so 2p6. Then comes 3s, 3s2, then 3p, 3p4, because then only you can get 16, 2, 2, 4, 4, 6, 10, 12, 16, right. So 1s2, 2s2, 2p6, 3s2, 3p4. So likewise you can write. Then let's say titanium 22. That is 1s2, 2s2, 2p6, 3s2, 3p6. Then after 3p, before writing 3d, we have 4s. So it is 4s2, 3d2. Right? 4s2, 3d2. Likewise, we can write, let's say Fe 26. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. Like that we can write the electronic configuration of any atom. Right. Now that's how we normally write the electronic configuration, but there are special cases for chromium and copper. So let's see what is that, the special case of the electronic configuration for chromium and copper. Now for chromium 24, our expected electronic configuration is like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. That's how the 24 comes. But if we write the actual one, what happens here is 4s2, 3d4 is like this: 4s2, 3d4, 1, 2, 3, 4. Having 4 orbitals filled is less stable. If electron of 4s can go to here, it becomes more stable. So, it tend to have 4s1 3d5. So, the actual one would be 1s2 2s2 2p6 3s2 3p6 4s1 3d5. So, that is the actual electronic configuration of chromium 4s1 3d5, right. So, it is very important to remember for chromium it is 4s1 3d5, not 4s2 3d4. Then special electronic configuration of copper is there 29. So, actual one would be expected one for the chromium would be same as earlier 1s2 2s2 2p6 3s2 3p6 4s2 3d9. So, again rather than having 3d9 it tend to becomes 3d10, which is more stable. So, the actual one would be 1s2 2s2 2p6 3s2 3p6 4s1 3d10. So, that is important to memorize. The chromium and copper has special electronic configuration. Not only for chromium and copper, down the group of chromium and copper they also have the same thing. So, the molybdenum and silver, down the group of chromium and copper, they also have the similar kind of electronic configuration. So, molybdenum tend to have 5s1 4d5, silver tend to have 5s1 4d10, right. They have not asked those stuff, but this stuff they have asked. So, that is the how we can write the electronic configuration of atoms. There are cases sometimes rather than writing all of these stuff, this is equal to argon. So, we write the electronic configuration of argon 4s1 3d10. We can write like that as well. Here also argon 4s1 3d5. We can write it like this as well, right. So, there are cases that we use like that. Okay. Last part, how we can write the electronic configuration of ions. Now, this is for atoms. How do we write the electronic configuration of ions? Now, when we talk about the ions, ions tend to remove or gain electrons. When electrons are removed, they form positive ions. When electrons are gained, they form negative ions. So, for the negative ions, it is very easy because electrons are just filling according to the Aufbau principle. For example, nitrogen 7, nitride is 7, but N3 minus. So, nitrogen is 1s2, 2s2, 2p3. So, nitride then you have to add 3 more electrons because negative ions mean electrons are being added 1s2, 2s2, 2p6. It is very easy. One more, sulfur 16, sulfide. So, 16 plus 2. So, 1s2, 2s2, 2p6. 3s2, 3p6. So, that is how the electronic configuration of negative ions, that is how we write the electronic configuration of negative ions. You have to just follow the Aufbau principle, right. The electronic configuration of positive ions gets slightly differ because when electrons are being filled, they are filled according to the when positive ions are formed, they are forming by removing electrons. When electrons are removed, they are removed always from the outermost subshell, not according to the Aufbau principle. This is mainly applicable for elements after atomic number 20. So, we call them as transition elements. For example, for sodium, it does not matter. Sodium is 11, 1s2, 2s2, 2p6, 3s1. So, sodium plus would be 1s2, 2s2, 2p6. That is it. That is fine. But when you write to the transition elements, let us say titanium, the same thing we wrote 22. Titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. When titanium forms, let us say titanium 3 plus ion, it is not like this 1s2, 2. So, I will write the everything up to here as argon. So, it is not like argon 4s2 3 4 3 electrons have been removed. It's not like, okay, first we write titanium 2 plus, it's not 4s2 3d0. That is wrong. Why? Always electrons are removed from outermost main subshell. So, titanium 2 plus would be argon 4s1 3d, sorry, 4s0 3d2. So, no need to write 4s0, we can write it as argon 3d10 3d2 like that. Okay. So, we will write another one. Positive ions are the one which you have to actually find. So, let us say chromium 3 plus. So, actually chromium is how? Chromium normally comes like this. Chromium is up to argon. I told it has special electronic configuration 4s1 3d5. So, chromium 3 plus means first electrons are removed from the outermost main energy level, which is 4 is first removed, then 3d. So, argon is fine, then 1 from 4s, so 4s0, 2 from 3d, 3d3. So, no need to write 4s0, you can write argon 3d3. So, that is how we write the electronic configuration of positive ions. Remember, when electrons are removed to make positive ions, always electrons are removed from the outermost subshell, but not according to the Aufbau principle, right. So, that is how we write the electronic configuration. So, that if this is helpful, give a thumbs up and consider subscribing. Thanks for watching.